So today we'll explain a bit of basics for the number theory and combinatorics, competitive programming. We'll go over some of the basics, and we also hope that from there you can also try to learn some other things. But there are some important topics that are very common even in introductory problems in competitions, and we will try to explain those. First, we'll start with number theory, and the first topic that maybe the first idea of this type of problems that may appear in competitions is how you can calculate the divisors of a number. As you know, every natural number has a set of divisors, and which obviously include the 1 and the number itself. How can you calculate this? So the most common algorithm to do this, it works in square root of n complexity. Now we'll go over why it is the square root of n. This is the actual code to implement this idea. It is in C++. So the main idea that I want to explain about calculating divisors is that you can notice that whenever you divide a number by its divisor, one of the two dividends will always be less. Let's assume that for now that we are not taking a perfect square. So for example, number 20. Whenever we divide 20 by one of its divisor, we notice that one of the two dividend or one of the two dividends will always be either below or above square root. For example, if you take 20, we divide it by 4. We know that 4 is below square root of 20, but 5 is above square root of 20. It means that if we iterate up to square root of n divisors, we can always find the other divisor, which is bigger than square root of n. That's the main idea that we use in the algorithm to find divisors. So what we do is we iterate from 1 to until I is less or equal to square root of n. Then we check whether n is divisible by I. So if I is a divisor of n, this is a C++ way to say basically if the remainder of division is 0, then we can maybe consider this as a divisor. So we know that I is a divisor, but it's possible that n is a perfect square and n divided by I is equal to I. Then we just add I to the list of divisors, so we do not add to I the same number. Then here we will, in case this is not a perfect square and this is not the actual square root, we will add both I and n divided by I. This guarantees that in the square root time we can have all the divisors of a number. This is a pretty simple algorithm, but it's actually very important in many even easier problems to understand how to calculate divisors in square root of n. So then the next concept, which is probably a concept that is very widely known, the idea of prime numbers. So prime numbers, as you may know, are numbers that only have two divisors, which are 1 and the number itself. Prime numbers are very important in number theory, but also of course in competitive programming, even in easier problems. It's a key concept, like I said, in number theory. Why is that? So now prime numbers have only two divisors, and some other property is that all the primes are odd except 2. This also is an important fact we will expand later. And the most naive way to check whether a number is prime is by using the previous algorithm. So we can find maybe the divisors of a certain prime number and check if the divisors are only 1 and the number itself. So if it has two divisors, 1 and the number itself, then it obviously is a prime. And this is square root of n, but there is actually, there are other ways to find whether a number is prime or not. And we see a more efficient way in the next slides, which uses a very interesting idea. So regarding prime numbers, there are certain conjectures, meaning that there are certain properties that are not, certain claims that are not proven to work in a rigorous way, but they work up to very large numbers, so we can use them in competitions. The first one, which is the most used, is the Goldbach conjecture. It says that each even integer can be represented as the sum of two prime numbers. And since the sum of two odd numbers is always even, so given this conjecture, we can solve certain problems where maybe we have to actually find this. In my experience, it happens sometimes that in certain problems this has been actually useful. Then the other two are not that common, but I'd say maybe the Legendre's conjecture. I've seen it once before, and it says that there is a prime between n squared and plus 1 squared, but the last two are not very common. The first one is more important. It's just something to know that maybe in some problem may help to find a certain observation. So now we go to a more interesting topic, which is the factorization. As you may know, every number not a number greater than 1 has a unique prime factorization, which is a way to write a number as a product of certain number of primes elevated to their exponent, respective exponent in the factorization. So if, for example, here you can see that 84 can be represented as 2 to the power 2, 3, and 7 to the power 1. And this representation as distinct prime numbers is unique if we take a number natural number which is greater than 1. Of course, this is also very important in many problems. It appears a lot. Knowing how to use prime factories, how it works, but also how to find it. And how to find it in reasonable time, it's actually a not naive problem. So we'll explain now how to do it maybe later. So another concept that you may know is the like the greatest common divisor, least common multiplier of two numbers. Greatest common divisor, of course, is the greatest number that divides both a and b. Least common multiple is the lowest multiple that is a multiple of both a and b. These two functions are actually have an interesting link to each other because you can calculate the SCM with the GCD. Actually, the GCD is already implemented in many languages. C++ has the function GCD. You can actually find it on your own with the extended Euclidean algorithm, but it's not needed to just calculate GCD. And you can derive the SCM from the GCD. So these are other interesting properties about GCD. GCD of 0A is A, GCD of A is A, and GCD AB is equal to GCD of B of A. So another interesting fact that is widely known is that if you take the prime factorization of two numbers, you can actually find the GCD and SCM without using Euclidean algorithm or anything. For GCD, you know that for two numbers, you take the common prime factors with the lowest exponent. For example, if you have a number that has 2 to the power 3, another one has 2 to the power 1, you take 2 to the power 1 because it means that that number divides both a and b, and it's the biggest possible exponent that you can take. Otherwise, it will not divide the, let's say, number that has 2 to the power 1, for example. And for SCM, you take, with the same idea, you take all the factors that you can find in the two numbers, two or more numbers, but in this case, we're considering two numbers, with the highest possible exponent. So an important algorithm that is which you can use to find whether a number is prime, but also you can use it in other ways, is the sieve of Eratosthenes, also known as sieve generally. It's an algorithm to check whether, if you take a range from 2 to n, with this algorithm you can check whether a number is a prime, but also you can check what is the smallest prime divisor of this number. So, and the fact is this algorithm work in n log n, which is very close to n, so it's very fast. But this algorithm generally used in pre-processing. It means that you need to, in certain problems, maybe you know that maximum number that you can have is 10 to the power 5. Then you can do this pre-processing from 2 to 10 to the power 5. But this obviously you will find this more in when you solve problems with sieve. The idea of the algorithm is that you start from 2, then you go from 2 to n. Whenever you find, so initially this array sieve, which is size n, all of them will be false. Okay. Then whenever you find a prime, so the first value that we'll find when you check function 2n is true, which is a prime, and sieve of x will be false. Then you will iterate to all the multiples of true, and you will set sieve of this value u, which is a multiple of true for in this case, as true. So you know that the smallest prime factor is true. Then you go to 3. We have the 3 is still false. Sieve of true is still false because it's a prime. We have not visited before in this nested loop, and we will do the same for 3. This way, with this iteration, for each prime, we will set all of its multiples that have not been visited before. We will set their sieve value, which is the smallest prime factor. And this allows us to know which numbers are prime, because the prime will not be visited by any other smaller value, because they're primes. They don't have divisors that are not 1 or the number itself. And this will allow us to find also the smallest prime divisor, which is useful in finding prime factorization, which we will see later. But this is the main idea of the algorithm. The interesting thing is understanding why this algorithm is not quadratic. Why is it n log n? The idea is that there is actual formula to find this out, but you can prove that this loop is actually very fast, because you only iterate through multiples of prime numbers, which is log n then in this case. Then the proof is a bit more complicated, but you can trust me for now that this is not quadratic, but this is n log n, so it's very fast. But it's generally used in preprocessing. So this is what is the resulting array if you take C from true to 20. So you can see that true of the sieve array of true is 0, because we will visit true the first time, and it's 0. Then what we do is we iterate for multiples in the nested loop for the multiples of true, which are 4, 6, 8, 10, 12, and all of those. And we will set generally the sieve of this array as these numbers. Actually, this array is actually not correct. It actually uses a different idea. But like this way, this array it's constructed in a way that it will not find which is the smallest prime factor, but just find any prime factor. So, for example, in this case, if you go to 3 to 6, technically the way I implemented here should be true. So the way I implemented, I start from true, then I will go through multiples of true in the nested loop and set the value of their index in the array as true. So we know that the smallest prime factor of 6, 8, 10, and 12, for example, is true. Then we go to the same for 3, but we will skip through all the values that we have already visited before. So this is more clear if you try to implement it, because then you will see what is the idea. But depending on how you want to implement sieve, the important thing is that you know which numbers are primes, and for those that are not primes, you can find maybe the smallest divisor, prime divisor, or maybe any prime divisor. So then how can you find the prime factorization of a number using sieve? Assuming that sieve array has for each value the smallest prime divisor, or 0 if it is a prime. What you do basically is that you take your number x. If it is 1, you just return the empty array. The 1 does not have a unique prime factorization. Otherwise, until we know that x is different than 0, if sieve of x is 0, which we know it means that it's a prime, then we just push this to the array and set x as 0. So then in the next iteration, we just exit the while loop. Otherwise, what we do is we divide x by its smallest prime factor. We put this factor in the primes array, and we divide x by this prime factor. It means that we remove this prime factor from the factorization. This is actually, again, more clear if you try to maybe write the process, but it's actually a lot more simpler than it looks. Then the resulting array primes will have all the primes that divide the number x. For example, if you take 10, it will have true. We know that 10 is 4 multiplied by 5. So in the first iteration, we'll add true to primes, then true again to primes, then 5. And we'll add all the prime factors in this array. Then you can also maybe instead of using a vector, which is an array in C++, you can use maybe a map, have for each prime factor its power. You can do it in many ways. Maybe in some problems you need to know the distinct prime values, then you can use a set, depending on what you need in a problem. But this is the general idea on how to find the prime factorization using sieve. And again, this algorithm is very fast because basically then you can prove that the number of operations is bounded by log of n.
Sorry.
Yeah.
I have a question. So the sieve function returns 0 if the x is a prime number, and if not, it returns the smallest prime factor of x.
This one, right? The sieve function. You mean sieve of a certain index?
Sorry?
You mean sieve of a certain index?
No, I mean the sieve of a number.
Yeah, okay. So depending on the implementation, so in this case, so actually when I was explaining this, I was referring to an implementation where sieve of x is the smallest prime divisor of a number. Otherwise 0 or 1 is the same if it does not have a, if it's a prime, okay? In this case, it's a bit different. It's an implementation where you just take where sieve of x is 0 if it's a prime, otherwise it's just any prime divisor. But the way I think it's more useful if you take sieve of x as the smallest prime divisor, or 1 or 0 if it's a prime, it's the same. So you can say it's 0 if it's a prime, or otherwise the smallest prime divisor. Because then you can use it in this algorithm to find the factorization. Okay. Okay, then we'll go over briefly to some modular arithmetic concepts. Modular arithmetic is it's actually very important topic because it's actually expected even in easier problems. It also has a lot of application in cryptography. It is also in abstract algebra and other topics in mathematics, or the area of mathematics. But for competitive programming purposes, you don't need to know a lot of stuff. For easier problems, you may not only need to know the fundamentals, and we'll go over those briefly. So what is the idea of modular arithmetic? Is that it is the branch of arithmetic which focuses on the reminders of divisions. You can see here, let's look at this. So you can see here, this is probably something that you already studied in school, but when you divide a number by another number, if the number is divisible by this other, then the remainder will be 0. It means that it's that other number, the dividend is a divisor of the like the number that we want to divide. So for example, here we see that 4 modulo 4 is 0 because 4 is a multiple of itself. 8 modulo 4 is 0 because the remainder of 8 divided by 4 is 0. But in other situations, for example, if you take 5 divided by 4, if we think about this division in, like for example, in the natural number, set of natural numbers of integer numbers, then this division, the answer is 1, but you have a remainder, which is 1. It means that if we divide 5 by 4, we'll get 1, but if we add another 1, we'll get 5. And then this is the same idea that you probably already know from school, but just basically the modulo is the remainder of the division. This is maybe the easier way to write the operation, but generally in mathematics, I think this is the most common way, which you write the number that you want to divide. Then the modulo is that the divisor, the dividend, sorry. So it means that we try to divide 131 by 3, and the 2 is the remainder. And the way we actually say this equation, this is called a congruence equation, and we say that 131 is congruent to 2 modulo 3. So if we divide 131 by 3, we'll get a remainder of 2. So you can see that we don't care what is the actual answer of the division, but only the remainder of the division. And then how to do this in a language? In C++ is just the percent operator, as I showed before here. this n% I is basically what is the remainder of the division between n and I. This is the how to implement the modulo operator in C++, for example, but it should be the same in other languages. So we just all go over through properties. There are many more others. Also, there is the case when you have negative values, which is slightly more complicated. And but generally, these two are very basic properties that a plus b modulo m is equal to a modulo m plus b modulo m modulo m, and the same is for multiplications. These two are important because in some problems, especially in combinatorics problems or dynamic programming problems, since generally the answer can be very big in counting problems, you are asked to find the answer modulo something. This you will see this in problem, especially at a certain level, maybe code force division to CD level or more, is that you will be asked to find the answer modulo something. Generally, it's modulo 10 to the power 9 plus 7 or something like that. That means that you need to get your answer and apply modulo operator and find which is the remainder of the division. The way to do that is basically you just, whenever you add the true values in constructing your answer, or you multiply true values while you're constructing your answer, you apply the modulo operator at every intermediate step, because these properties allow you to do this. But you will see this also in when you get to problems that require modulo. But generally, it's like I said, division through code forces C, so it's not very, very early, I think. And okay, that's mostly it for number theory fundamentals. There are also many, many other things that are more advanced, but I think these are the fundamental basics for up to a very far point in competitive programming. You just need mostly this stuff. Then in division 1 code forces, maybe of course you need many other things, but for now I think these are the important basics. And also I advise you to try to understand on your own why this is the complexity of these operations, because it's important to know, I think, but you need to actually read the proof for it and try to actually understand why. And yeah, that's mostly it. You have any questions on this part? Otherwise we can move to a bit of combinatorics. Okay, let's see if it's recording. Okay, let's record.
Okay, combinatorics. Combinatorics is generally about counting number of ways of something. So it's more about counting, and I think graphs in mathematics is a part of combinatorics. But it's generally we discuss about calculating many things. Okay, first thing. Permutations and factorials. The first thing is that permutation is an array with distinct elements in some arbitrary order. So, and we have n factorial permutation. N factorial means 1 to n multiplied by each other. So we have n factorial different permutations. It's a simple thing. And after that, we have some kind of calculating combinatorics. So, what would happen if we have an array of numbers 1 to n, but only r elements, r numbers, which are already chosen. For example, 1 to r can have the order change. So all of the other numbers would be in the same position as before, so it would have the some kind of we would have some permutations. The number of them would be r factorial, but we also have other problems, which one of them is represented here. Okay. This is another problem, and the number of permutations when you have taken r numbers at the time would be n factorial divided by n minus r factorial, because you don't consider the n minus r other numbers permutations, because it's not important. You don't want to count twice, so you divide n factorial by that because you counted every situation n minus r factorial. And after that we have binomial coefficients, which is actually a combination of n and k, which means the thing I'm going to describe. Choosing k from n means that we have a set of n different things, different elements, and we want to choose k elements from that. So how many possible choosing would be there? So how many ways are there? That's actually binomial coefficient, and we call it a combination of n and k, or choosing k element from n. So that's the thing we are describing here. For example, we have 10 possible ways to choose 3 numbers out of 5 numbers, which means 3 choose 5 or something like that would be 10. So it's the definition of that, and we want to calculate that. Okay, how we can calculate the number of ways to choose k numbers out of n? The first thing is that we can calculate by this formula, and where did this formula came from? It's actually from, you choose an arbitrary permutation of all the numbers, okay, and you decide to only pick k first elements. So you will choose an arbitrary permutation, and you will only choose k first elements, okay, and that would be n factorial. But for each possible way, we counted that way k factorial multiplied by n minus k factorial. Why? Because when we are choosing these k numbers, the order of these k first numbers would not be important, so it's not important for us, so we are actually considering that for nothing. So we counted every way k factorial times, and apart from that, if you see other numbers, the remaining numbers, their order is not important, so we should also cancel that. So we can conclude that we counted every possible ways to choose k numbers from n numbers, k factorial multiplied by n minus k factorial. So easily choosing k from n would be n factorial divided by k factorial, and another time divided by n minus k factorial. Okay, we have a coin, and we, out of 10 times, this is a problem. We want to get the probability of getting exactly 4 heads when we toss a coin 10 times. What would be the answer? Okay, do you have any idea how to solve it? So
10 choose 4.
yeah, exactly. So we know that if we write down every time head or tail, so we have an array of h and t of length of 10, and we want number of ways that only 4 of them are h. So we can choose 4 out of that 10 to be the heads appeared in this procedure. And so these are the number of valid things that we want to count, and because it's probability, we should divide it by all the possible ways. And how much would be that?
It's
How many different situations may came out when we toss a coin 10 times? Hmm?
you mean also the different possibilities and also the order of the outcomes?
No, the order is not important. So we know that we have an array that each element is h or t, representing head or tail, because we toss the coin 10 times. So how many different arrays would we have?
2 to the 10.
Yeah, 2 to the power. And that would be easily a simple problem that used binomial coefficient, or we call it combination. And yeah, that's the solution. And probability would be something around 20%. Okay. Calculation of combination. First method. There's a formula. I think the formula was Pascal's formula. It's the thing we have there. So, choosing k elements out of n elements would be equal to summing up these two things. The first one is k minus 1 of n minus 1, and the other thing is k from n minus 1. So that's a simple formula, but I want to prove it. The proof is not that hard. So we have a set of n elements, and we want to choose only k elements from that. Okay, let's see the last element of this array or these numbers. Okay, there are only two possible things for that. It's chosen or it's not chosen. So he's chosen. This number is chosen or not chosen. If it was chosen, out of n minus 1 remaining elements, we should choose k minus 1 element. So that would be easily combination of k minus 1 and n minus 1. If it was not chosen, we should choose k numbers out of the remaining numbers. So it would be combination of k combination of k and n minus 1. Choosing k out of n minus 1. And these are completely independent, so there is no thing which appeared in both of them, because we are considering the last element and saying it's chosen or not. So easily the choosing k out of n would be sum of these two things, and it would give us a possible way to calculating these binomial coefficients. How? It's kind of DP, dynamic programming. We have the base things. So we know that choosing 0 element out of n elements would be 1, because there is only one way to do that, not choosing anything. And choosing n out of n would be 1. And these are bases, and we can calculate all the others by that formula by iterating in the right way. I think in next slides we will see the actual code, and I will go in detail. The other formula is the one we already see, and that's that formula. And in competitive programming, if you have k factorial and factorial, you can calculate this, but sometimes you cannot use the last formula, and you should do this one. And sometimes the actual number of n factorial would be very large, so we would face overflow, and because of that, the problem set usually it happens that give the answer modulo some prime, some big prime, and for that kind of problem, we calculate the factorials in mode of something, and I will show you the code.
Just show us why not. How do, like in general, you will see. Thank you. Let's quickly show. Generally, the way most problems in general, you will be asked to calculate quantities like those with respect to a module, like I explained before, like a module or something. But so, for example, you know that n factorial will be, numerator will be this modulo something. Okay, this is clear. But what about the denominator? What you do is there is a concept called the modulo multiplicative inverse, which I did not explain before, but just show that there is a way to calculate that very easily. The way that the concept of the modulo inverse is that you calculate k factorial, the inverse modulo x, basically. So basically, you calculate the inverse factorial of k modulo x. And calculating this, you need to do, use some theorem in some algebra theorem, but just to show. And then what you do basically is multiply this, and minus k inverse factorial modulo x. So if you are asked to calculate that modulo something, you multiply n factorial modulo x, inverse factorial of k modulo x, inverse factorial of n minus k modulo x. You multiply this. But this is, then if you're interested in actually knowing this, we'll maybe show it another time, just to show that it's possible to calculate it. That was it. But for now, it's not too important.
So multiplying all of that is interest k all that.
Yeah, basically you can, if you asked to do it modulo something, you can do that. And factorial of the modulo multiplied by k inverse factorial, the inverse factorial of k, and inverse factorial of n minus k. You multiply these three quantities, and you get that value. But this works if it's asked modulo something. Otherwise, I don't think you can do it this way.
Yeah. Okay. So, but if the numbers were very small, you can do it easily because the combination would not be large. Some other facts. The first thing is sum of choosing 0 to n from n would be 2 to power n. Do you have any idea why is it true?
Because it's like it is all the subsets that are contained in a given set.
Mm-hmm.
And that's the power set, which is 2 to the power n. So basically doing n choose 0, n choose 1, and so on gives all the possible combinations.
Yeah, that's true. So the thing was mentioned is that we have a set of n numbers, and we want to know number of subsets, which would be 2 to power n. And in the left side, we have number of subsets with 0, with length of 0, the size of 0, plus number of subsets with size of 1, size of 2, till size of n. So every subset would be calculated. And we also have the second one, which is, that's why the name of this is binomial coefficients, because if you see that formula, you can understand that binomial coefficients are needed. A plus b to power n, what it would be if we sit on the right side. For example, we have a to power k and b to power n minus k. How many times we uh, like sum this thing in the answer? It would be exactly choosing k parentheses to give us a and others to give us b. So it would be choosing k out of n. So that would be the coefficient of the a to power k multiplied by b to power n minus k. Because in the left side we would have n parentheses with a plus b inside them, and from each one of them we should choose to get a or b. And that's it. The second one is not that useful in competitive programming, but just knowing that would be good. We also have other things, I think Pascal triangle, something like that.
Anymore. Yeah. I think Pascal. I think Pascal and also this last one can be useful in harder programming where maybe you actually need to do some calculations to find some observation. But the first one is I think first one is actually more important. It's pretty common.
Yep. Okay. Problem. So we are here in a grid. Our home is here, and we want to go to somewhere. In this example, the problem asks you to calculate number of ways that you can go from your home to health club. The only possible direction you can go is one step to the right or one step to the up. And because of that, you cannot go left and down, so you cannot go out of this rectangle. So the problem asks for number of ways to do that. We can wait a little bit to think on it.
Should we choose to the power n plus n?
No, why not? I will give you an example. For example, this grid. In this grid, you said this is n, so we should go n steps to the up and n steps to the right. You said 2 to power n plus n.
Okay, it's wrong.
Yeah, it's right because you can. One of the things you are considering in this thing is going up n plus m times, and that would be out of our way. So that's not the answer. Any other idea? As a hint, I can say something. Let's consider that we have a robot that's doing some orders. So, going from here to there would be a string of orders having the length of n plus n, which is number of up and right steps needed, and each element would be u or r that represent up or right, and the robot would follow this string to go from home to somewhere. And you are asked to calculate number of value strings that would if the robot follows that, he would be in the health club at the end from the home.
Yeah, I'm trying to visualize the problem in this way, but I struggle to find a form. So I'm thinking, for example, the first instruction can be just up or right, for example. Then if we can, for example, go up for n times, and then we must go all to the right for the rest of the instructions. But I don't know. I am thinking about the correct form.
We can wait a little bit. Okay. Let's. Do you see in this string? Do you see any specific property that this string should have to be valid for us? For example, the first thing is the length of that should be n plus n.
Yeah, of course. And then we should have the command up n times and the command right n times. That's we are going to do.
Exactly. So we want to calculate number of arrays that have this thing. Do you have any idea how? These properties. The thing is like that. So we have an array. Let's consider that big
It's
N.
similar to the problem of the toast coin in some sense.
Actually, it's like the combination, the binomial coefficient. As a hint. So let's have the big N as n plus m, the total steps needed. That would be the Manhattan distance of home and health club. And we want m of these elements, these characters in a string, to be up, and all others would be right. So it's similar to which problem that we saw recently?
The toast coin. The toast coin.
Yeah, exactly. So we have an array of big N elements, and we want to choose m elements to be r and to be up anything, and others would be easily the other character. So that would be, the answer would be combination of m and n, number of choosing m numbers out of n numbers. Okay, so the problem would be this combination. So for example, here we need five up steps and 8 right steps. So the answer would be, I wrote the combination of the things, so it would be choosing 5 out of 13. I should correct that. Yeah, but it means 5 out of 13 upside down.
But I don't understand why is 13 choose 8 equal to.
It's actually it's upside down, so it's 8 choosing 8 from 13. Okay. Maybe I didn't get your question. But if your question is why the choosing 8 elements from 13 would be equal to choosing 5 elements out of 13, because, for example, in the coin problem, we could choose 4 of them to be head, as we did, and others would be tail, or we can choose
6
tail, yeah, and other would be head. And these are equal, no matter how you decide. Did you understand now?
Yeah.
Yeah.
I thought about this, but that was my doubt, because I was tempted to say, for example, n plus m, choose n, but at the same time I was questioning myself, like, and then why can't it be n plus m choose n? But it's the same thing, so okay.
Okay, great. So just for the recording, this thing is upside down, so I mean that choosing 8 from 13, not 13 from 8, because 13 from 8 would be 0. Very stupid mistake. And final code. Okay. You can calculate number of combination of k and n easily like that. Recursive function, and that would be the formula we saw before. So if the k equal to 0 or k equals to n, the answer is simply 1. But if it was not the case, the answer would be k minus 1, choosing k minus 1 out of n minus 1, plus choosing k out of n minus 1. That was the formula we saw in the slides. So is it clear? It's a recursive function. And we can also implement that thing with arrays. It's a dynamic programming way, just to mention. So the base things are when the n equals to 0, so this thing. Cij means that choosing I elements, choosing j elements from a set of size I. Okay, so choosing j element out of I. Simply choosing 0 element out of I elements would be 1 for every number. And after that, for calculating other ends, we already calculated the C function for the I equal to 0, because we know that C0, there is only C00, which is 1, and we calculated it here. Okay, so here we should calculate C for other ends, for other i's here. So we iterated from 1 to n in I, and for each j, we calculated C, I, and J like that. And the thing I want to mention here is that when you are updating your CI and J, the things you are getting updated from, so the things after equal sign, should be calculated before. Here you can see that they are already calculated. Why? Because there is I minus 1 in both of them, and I, the elements which have the first part, I minus 1, are calculated before when you are seeing the I. They are in previous steps they are calculated. So is it clear?
For now, well, no, I mean, I have to get currently at home.
Oh, okay. No problem. But the thing I mentioned, just have it in mind that here the things are already calculated when you are seeing this thing. Because they are in previous steps. They have I minus 1, they have the first element less than ours. And answer would be
because it is like a recursive solution or something.
Yeah, it's a recursive, but we did it dynamic programming way.
Okay.
Yeah, it's a typical way to do this, and it's very important. And this is actually the beginning of dynamic programming. So read it carefully and learn it carefully. So it would be useful in the future. This trick. And also the thing I mentioned, you can see here that there's a mode. Why there's a mode in the, because sometimes, for example, when you have the maximum n up to 1000, choosing 500 out of 1000 would be a very large number. You can imagine how large it would be because it has elements like this: 1000 multiplied by 999 up to 501. So these numbers are in the denominator, and the others would be 500 still one in the denominator. So that would be a very large number, something you can easily see that it's more than 2 to power 500, so that would be easily overflow. And because of that, the problem state that give the answer modulo 1e9 plus 7, which is a prime. So here we easily only added mod sign %, and we did it every time we calculated something. That was the thing Ghassan mentioned before. Okay, another problem. Number of subarrays of an array. Subarray is array which is constitutive. So every element of that came after each other, right after each other. So you choose a block partition, something like that. That would be the definition of subarray. That's the subarray. What would be the number of subarrays? That would be exactly like that. This formula. We can see this problem as like this. First, I would explain in some naive solution, and then I would give the smart solution. How many subarrays would start from the first element? So how many subarrays have the left point in the first element?
N minus 1.
N, because you should also consider the array which has only the first element.
Okay.
So the right point could be in n point. So it would be n. What about subarrays that would be started from the second position? N minus 1. And the third position, n minus 2. Up to how many subarrays would start at the end position? That would be easily 1, because they should be ended right there. So that would be numbers n minus 1 and minus 2 to 1 added together. So the answer would be adding up these numbers, which would be by the formula n multiplied by n plus 1 divided by 2. Is it clear?
Yeah.
Okay, but that was a naive solution. Let's give the smart solution. Let me think. Do you have any idea how we can get the choosing 2 out of n plus 1 directly without summing up these things? This one is actually very tricky one. Just look at here. So just look at where the endpoints could be. So it could be between 1 and 2, between 2 and 3, between 3 and 4, after 4, before 1. Okay. Simply here for numbers 1 to 4, we have 5 possible positions. If we choose any 2 of them, so if you choose any 2 of them, for example this one and this one, it would give you a non-empty subarray. For example, this one can give this. So how many positions do we have? N plus 1. And if you choose 2 out of them, any of that 2 would give you a subarray, which has the length at least equal to 1. And so that would be exactly the solution. In the smart way, we can call it something like that. So that would be the up to the point solution. Choosing 2 out of n plus 1. Yes. The next thing is subsequences. Subsequences could be in different positions. They are not under obligation to be. They shouldn't be right after each other. They could be. They could be some free spaces between them, between the elements you choose from the array. So, for example, here from array 2734165, you can choose 7315. That's a subsequence. How many subsequences do we have? 2 to power n, because you can choose each number to be present at the subsequence or not. But there is a thing you should consider. With considering 2 to power n, you also consider the empty subsequence. It's possible to get it's also possible to get empty subsequence. So if the problem asks for non-empty subsequences, you should just add n minus 1. That was it. And the last thing is the principle of inclusion and exclusion. I think we already had it. And this thing, for example, let's consider that we have 2 conditions on something. So condition A and condition B. So if you consider the whole space, some of things would be in this circle of A under condition A, and some of them may not. And some of them may be under the condition B, and some of them may not. But if the problem asks how many things in this space are under both of them, you should consider the uh, in intersection of them. So you should consider the things in their intersection. And so that would be, if you wanted to, that would be one problem, okay? And the other thing, for example, they ask you how many things in this space have at least one of these properties. That would be easily number of these things here. But if you add number of things having the first one plus number of things having the second one, you counted some of them, exactly the intersection twice. So you should exclude it once. That's a simple thing. And yeah, any question? Okay, and it could also be in with 3 or more conditions. The sample problem of that would be, let's imagine that we have numbers up to 100. The first condition is to be dividable by 2, and the second one is by 3. For example, in this one, the third one would be by 5. And the problems ask you something, so you should be careful with not calculating, not counting the numbers twice. It's quite logical. And that was the end. Okay, thank you for your attention.